Okay, so for part one of homework 4-1 here, hopefully going to move through this fairly quickly. On the multiple choice questions, just making sure you're paying attention to which one is which, right? So consider a plot of the displacement as a function of the applied force. And it is actually very important we pay attention to which way that's read. If I'm thinking of the displacement as a function of the force, then what this is saying is the displacement is acting as my y variable and the force is acting as my x variable. So I've got a x versus force graph, right? And then what would the slope of this be? Well, if I was looking at a graph like this, right, what would the slope be? Well, I know the relationship between x and f, right? F equals kx is the relationship I'm hopefully thinking, because that's the relationship between force and displacement. If it was solved for x, right, if it was solved for the output variable, my y variable, then it would be x equals 1 over k times f. So if I think about it this way, if I just again solve that to get x by itself, then now x is my dependent variable, right? It depends on f. So this is acting as my y, this is acting as my x, which means my slope is 1 over k. So it's the reciprocal of the spring constant if I've graphed these two as a function of time versus, or as a function of each other. Right, so if I do the position as a function of force, it's 1 over the reciprocal, or it's 1 over the spring constant. If I did the force as a function of the displacement, then it would just be the spring constant. Question 2 and 3, obviously mind the fact that they're not ordered correctly. I know A, C, and then B, and then D. Just the way that I screenshotted these, got the images switched around, but that's okay. So anyway, which of the graphs best illustrates Hooke's law? Well, Hooke's law, again, we need to realize that's just simply force equals negative kx, which would be a linear relationship, right? If I'm doing force versus displacement, it would be a linear relationship. So I can rule out B and D. And then obviously as x increases, as x gets bigger, the force would vary as well. So C, the second choice here, C is my best option for question 2. Question 3 is a slightly trickier variation of question 2. Which graph best represents a spring that gets less stiff as it's more stretched? So if it gets less stiff, then the constant would be decreasing over time. Well, the biggest thing to recognize there is on a force versus displacement graph, my slope is my constant. So if the constant is decreasing, then my slope needs to be decreasing as I go further and further. Right? So A and C are obviously not right because they have constant slopes, which doesn't make any sense for this problem where it's varying. B, the problem with B is the slope is getting steeper, which would mean the spring would be getting more and more stiff as you stretch it more and more. So B is not right, so D is the correct option for that one. As you stretch it more, it gets less stiff, and therefore the slope is decreasing over time. Question 4. Yes, it is possible to have negative potential energy, because keep in mind potential energy is always relative to whatever I want it to be relative to. So we've seen problems in the past where, for instance, if I hold an object up here, but I ask you what's the potential energy with respect to the ceiling, it is negative potential energy with respect to the ceiling. So yes, it is possible, since the choice of our 0 is completely arbitrary. I can choose whatever point I want to be 0. If I choose the ceiling to be 0, then this would be below the ceiling, so that's why I would have negative potential energy. Question 5, hopefully a pretty easy question here. Just make sure you are watching your units, right? It is centimeters, so 0.21 meters, and then later 0.31 meters. But in this case, it's pretty much being comfortable with what's happening, right? So what is the weight of the fish, or what is the weight of the fish that would cause it to stretch 31 centimeters? So you've taken a spring, you've hung a fish from that spring, and it's caused it to stretch 21 centimeters if it weighs 135 newtons. Well, really the only relationship we have to be comfortable with here is the fact that the spring force is going to be equal and opposite to the gravitational force once it's stretched, right? That's the reason that the spring is stretching, is so that the spring force can balance out gravity. So it's really just that relationship. So by taking advantage of the initial information they give me, I know kx equals mass times gravity. So by taking advantage of that, I can find my constant, which would then be the same for the second part of this question as well. So I've got my k times my, again, how far it's been stretched, so 0.21 initially, and then the entire mass times gravity. They've defined that whole thing for me as 135. So that allows me to find my constant, right? I can find my constant to be about 642.86. And then now that I know that constant, I can say, well, the force of gravity, right, again needs to equal the spring force. The weight of the object, the force of gravity of the object, would be that k, so 642.86, times that distance that is stretched the second time. So I end up getting that weight ends up being about 199 newtons. You could actually also set this up just using a proportionality. Since you know that F equals kx, then we know that k equals F over x. So since the k is constant, you could actually just set up the force of gravity for the first one over the displacement of the first one equal to the force of gravity for the second one over the displacement of the second one as well. Okay, so there's nothing wrong with solving it using this approach either, as long as you realize that you can do that only because k is constant. If the k varied, I wouldn't be able to use that approach. But anyway, hopefully not a bad question here for a question. Question 6 gives you a lot of information. They give you the initial velocity, the final velocity. They kind of leave it to where maybe there is friction, maybe there isn't friction. We're not 100% sure. But to be honest, if you read the actual question, it doesn't matter. The question is, how much work does gravity do on the block during this process? Regardless of whether there's friction or air resistance or anything else, the second they ask me how much work does gravity do makes this problem significantly easier. Because I know that the work done by gravity, right, the work done by gravity would be simply the force of gravity times the component down the ramp, or better yet, be simply the change in potential energy due to gravity, right? Whatever work is done by gravity, that's going to be whatever change in energy I've had for gravity. So all I really have to do is find my change in height, and that's going to be the work done by gravity, right? Or that's going to help me find the work done by gravity. So I'm going to say my work is simply my mass times gravity times my change in height. So then the work equals the mass, which they gave me, of 8, the gravity, which we know is always 9.8 unless we're on another planet, and then the only thing you have to be careful about is the height. Because it's 1.6 meters down the ramp, we would do 1.6 meters times the sine of 40, and that would represent the height, right, of the ramp. So then my work ends up just being 80.6 joules of energy. That's how much work gravity did as it pulled it down, right? I would leave that as a positive because in that sense it has moved downward, right? And gravity is pulling downward, so we know the work would be positive because those are both going in the same direction. And again, we're just looking at that change in energy. So hopefully nothing too crazy with question 6 here either. Question 7, once again, is a key relationship here, that work is simply a change in energy, right? So they give us the work that it took for us to pull the sister back, and really we just need to realize that that work is how much potential energy we've given her as we lift her to a higher location, right? So once you get that established, then there is a little bit of trig, right? There's a little bit of a triangle work we have to do here, but hopefully it's not a bad question. So we know that the swing itself is 5.10 meters long, which means that is always 5.10 meters long. As I pull it back to an angle of 32 degrees, I need to try to figure out what the vertical height of that would still be so that I can find my change in height, right? So all I'm going to do is take 5.10 times the cosine of 32, because that would tell me the vertical portion of that string at that moment. Right, so 5.10 times cosine of 32 ends up being about 4.33. So that tells me how many meters it's still hanging down, which gives me a route to now find the height. The height would just be 5.10 minus 4.33. So then my height ends up being, my change in height I should say, ends up being about 0.77 or 0.775, I think, if you take it out to another decimal place that I didn't show here. But in any case, about 0.77, 0.78, somewhere in that ballpark. So now I know that that's the change in height. They tell me that this was how much work went in, so that's my change in potential energy. So if I just use my potential energy equal to mass times gravity times my change in height, I know that 174 joules equals the mass, which is what I'm looking for, times the gravity of 9.8, times the change in height of 0.775, and I can find the mass of this sister here without too much trouble. So I find the mass and I get about 22.9 kilograms of mass. So anyway, as soon as I realize that it is a work-energy relationship, hopefully not a bad question to move through here. Okay, so question 8 here is a good question just to think about kind of equilibrium and what's happening. So they give us the unstretched lengths of 0.25. So in this first diagram where they say that it's actually stretched to 0.30, each of those springs has been stretched a little bit, which means each of those springs is exerting a force, right, pulling it back the other direction. But the key here is, since they both have the same constant and they've both been stretched the same amount, this would still be in equilibrium, and therefore, right, that's why that block can still just rest at that location. To be honest though, we really didn't need figure A to answer this question. They asked me for figure B, what is the force P that I need to exert to hold this block where it is? Well, they tell me that the distance D is 0.020 meters. So they've given me that distance there to work with. So then the biggest thing for this is just identifying what forces act on that second block, right, in figure B here. So again, they gave me that distance, which means this distance here would now be 0.28, whereas this distance here would be 0.32, right? Because I knew that initially L was 0.30, and then it says that I've pushed it off a distance to the right of 0.02. So it's compressed this distance to just 0.28, and it's stretched this one out to 0.32. However, the 0.28 is still longer than the spring's unstretched length, right? So the 0.28 with respect to the spring has actually still stretched it, so I'm going to call that delta x down here, but it's still stretched at a 0.03 meters past its unstretched length, its standard length. On this side, right, the standard length also 0.25 from what they gave me earlier. So this spring has now been stretched to a total stretch of 0.07 meters, right? So I need to just identify what forces act on that block. Well, if I think about it, because both of those springs have been stretched, they're still pulling back, right, towards themselves. So the spring on the right, which I'm going to call the second spring, so there'd be a force from that spring pulling off to the right. There would be a stronger force from the first spring pulling off to the left. And I know that that one would be stronger because it's been stretched more, right? So it'd be stretched further and it has the same K, so it's definitely a stronger one. Which is good, right? It's consistent with what I expect because I'm exerting another force P, which is what I'm looking for, that's also going off to the right. But if I'm holding this in place, then I know it's in equilibrium. So I know the net force is 0. And once I establish this relationship right here, it's a pretty easy question to solve. I know then that the spring force on that first one pulling back to the left would have to be equal and opposite to the second spring force plus that second exerted force, that exerted force P that I'm pushing off to the right with. So that's my relationship, that's my equilibrium relationship I want to take advantage of. And then it's just a matter of plugging everything in. So K times delta x1, which again is just 0.07 meters from its unstretched length, K times delta x2, which is 0.03 meters, and then I'm solving for that entire P. So 700 times 0.07 equals 700 times 0.03 plus P. So then solving for this, just subtracting that over and calculating, and I get that force needs to be about 28 newtons, needs to be exactly 28 newtons actually, to hold that one in place. So hopefully this question wasn't too bad either. And I think this is going to be where I stop part 1, just so I have enough time to thoroughly go into question 9 and then finish out the rest from there.